We're just asked to perform a partial fraction decomposition. Notice that the partial fraction is already set up for us. We have what we call a linear term in the denominator here, therefore we have a constant in the numerator. And in the next term we have a quadratic term in the denominator, therefore we have a linear numerator. Now to find a, b, and c, what I'm going to do is I'm going to multiply every single term by the original denominator. If we write all of this out, you'll notice that we get a whole lot of cancellation, and that's why we do it. Let's write down what's left after all of that cancellation. There are multiple ways to proceed from here. In the first video about partial fractions in this playlist, we chose specific values of x to plug into this equation. And it might be smart to do that here as well. You'll notice that if we choose x equals -1, this term over here is going to go to 0, and that's going to allow us to solve for a pretty quickly. Let's try it. On the left side of the equation, we get 9, I believe. And on the right side of the equation, the first term gives us 5 times a, and the second term is just going to give us 0. So really quickly, we have solved for a. If we divide both sides by 5, we get a equals 9/5. Okay, that's a great place to start. Now we could continue choosing values for x to plug into this equation. Notice that none are going to give us as simple a result as choosing x equals -1. So maybe I'll take this opportunity to show you another technique. Instead of choosing another x value, why don't we rewrite this equation here, but let's distribute out the right-hand side. Notice that after distributing out the right-hand side, we can group the terms on the right-hand side by powers on x. So we can group all the x squared terms together, all the x terms together, and all the constant terms together. If we do that, we get a line that looks like this. And now at this point, something that we can realize is that if this left-hand side is supposed to equal this right-hand side, the constants on x squared on the left side and the right side must match up. That gives us an equation right off the bat that 1 equals a plus b. Following that logic, the constants on the left and the right side of the equation on x must match up as well. In other words, we get an equation 4 equals b plus c. Doing that one more time, we notice that the constant on the left and the right side of the equation must match up as well. That gives us the equation 12 equals 4a plus c. Okay, well now we actually have more information than we need to solve this problem. If we just look at this first equation and remember that back at the beginning we had a equals 9/5, we can solve for b pretty quickly. 1 minus 9/5 is -4/5. We could then take that b equals -4/5 and plug it into this equation here. Solving for c means adding 4/5 to both sides, and 4 plus 4/5 is 24/5. That gives us all the information we need. If we wanted to check ourselves here, we could plug in a equals 9/5 over here, just to confirm that we get c equals 24/5. We do in fact get that result. We have completed the partial fraction problem to rewrite the original expression as a over x plus 1 plus bx plus c over x squared plus 4. And oh my gosh, I just realized that the problem asks us to actually evaluate the integral of this function. So okay, let's do it. The key here is splitting up the integral into 3 pieces. Integrating the first piece is just a natural log. The second piece here actually requires a u substitution. If you use u equals x squared plus 4, you'll notice that our x dx turns into 1/2 du. The integral then turns into 4/5 times 1/2 du over u. Well, that integral is just another natural log integral. If we bring the 1/2 outside, that turns our constant into a 2/5, and we get the natural log of u, which is x squared plus 4 for that integral. This last piece of the integral looks just like an inverse tangent integral with a equals 2. So integrating that is going to give us a 1/2 times the inverse tangent of x over 2. Bringing that 1/2 out in front is going to give us 12/5 times the inverse tangent of x over 2. And that is going to do it for that integral. I'm going to go to the top and I'm going to scroll through all of our work so you can take a second look at it and hit pause on your browser whenever you feel it's necessary. Okay, I hope that helped you out, and let's check out the next partial fraction video.